Good morning and welcome to the I-29 MOO University Dairy webinar series. Today we are going to visit about byproducts for dairy cows. Leading the discussion will be Dr. Paul Kononoff. He's with UNL, and he will review the options that producer have with byproduct feeds. Dr. Kononoff, a native of Saskatchewan, Canada, earned a B.S. and M.S. in animal science from University of Saskatchewan and Ph.D. from Pennsylvania State University. Has a world of experience and recognition as a dairy nutritionist, has worked for many companies, and since 2005 has been employed with University of Nebraska-Lincoln as the dairy nutrition extension specialist. Really needs no further introduction. Paul, the podium is yours.
Okay, good. Okay, thank you very much, Fred. So as Fred mentioned, my name is Paul Kononoff, but I also want to acknowledge a contributor for this presentation today, Addison Carroll, who's a PhD graduate student here at the University of Nebraska. So I think everybody knows, we used to use the old term byproducts, but corn, dried distillers grains are a byproduct. A new, more recent term is co-product. The definition of a co-product is a secondary product that is produced in addition to the principal product. That's a very simple definition, but I think it's important to understand that in many cases, when you think about a lot of these feeds, it's really a result of a commercial operation doing something else. And so the quality of that feed often depends upon what that business is doing. And corn ethanol is no different. A lot of the business decisions that are made in that operation affect the nutritional quality, for better or worse, on the final byproducts. When we think about co-products, there's a whole array of feeds, but today I'm going to specifically talk about corn distillers grains, which is probably the #1 co-product here in the Midwest and the Northern Plains. These are generally considered to be, many of them have a high concentration of nutrients. And in many cases, because these are coming from, co-products may come from the food industry or even the beverage industry, they tend to have a high palatability. And this is something I'll be sharing very briefly about. It's been some recent work we've done in this area. Co-products are very important to animal agriculture as a whole. If you're interested in maybe understanding the accounting of that and their role, I'd refer you to a paper by White and Hall that was published in 2017. On the left is an infographic just explaining where byproducts or co-products fit into this web of food production. They obviously serve as a source of feed for livestock. That's something we'll be talking about here. And through that, they contribute food to the public. Additionally, they also serve as a source of nutrients or fertilizer for production of more crops as well. On the right-hand side is just some of the accounting of these features, but just want to show just how intimately involved and integrated byproducts or co-products are for not only this country, but the world of food production. And they're certainly not new. They're certainly not only attached to the biofuel production, but byproducts or co-products are intimately involved in food production all over the world. So I mentioned early on that they're highly palatable. It's interesting when we see some of the responses with with co-products, we'll often remark that we think these feeds are highly palatable, but as we started to say that more and more, we realized aside from feed intake data, we really didn't have much information that actually tested and demonstrated the palatability of these ingredients. And so several years ago, we started using a procedure or a study design that was developed by Peter Erickson at the University of New Hampshire, and basically doing very simple studies where we'll offer animals on the right-hand side, you'll see, we'll offer them a series of feed ingredients and simply rank them. And how we do that is the studies go for about 9 days. And so on day 1, we'll offer them 4 feeds. And generally it's about 1 kilogram of that feed. And we observe what happens when the animals are offered those feeds. So this is just a video showing animals demonstrating preference for a particular feed ingredient. And so in this case, you can see this animal is preferring the feed that's labeled in the pink duct tape. And so what we'll do is we'll do that for several days, and then that most preferred feed is actually removed from the grid, and then the remaining 3 are offered. And then we find and we observe the next most preferred feed, and then so on. These have been a lot of fun to do. We've learned a lot of really important things about animal behavior, feed preference, and then obviously as it relates to nutrition and feed utilization. So in this study, we actually offered, as I mentioned, 4 ingredients. One was ground corn. The other one was corn, dried corn distillers grains. The third one was an animal protein. And then the fourth was a blend of all of the ingredients. And so what you see here listed here is actually all the data that we collected on each of the individual animals. But what I'll show you here is the ranking. And so our hypothesis was, and we've been saying for a long time, that distillers grains are often highly palatable. To my knowledge, this was, at least for our case, the first time we've actually tested this compared to other ingredients. And you'll see that the mean ranking for distillers grains for these animals was 1, showing us that these animals preferred distillers grains compared to those other ingredients. We've continued to use this type of study design and compare other feeds, but you can see here, at least based on the ingredients that were offered here, corn distillers grains was highly preferred by the animals. So what's in distillers grains and why do we feed it? I'm actually going to show you a lot of the experiments that I showed later in this presentation is going to be on protein, but I briefly want to talk about fiber and energy. David Combs at University of Wisconsin has done a lot of work on total track NDF digestibility, and I would refer you to the website here listed here, as well as his website if you're interested. He's developed a system that estimates NDF digestibility from in vitro, chemical composition of that feed, and then in vitro NDF digestibility. NDF is important because a 2 to 3% change in NDF digestibility should translate into roughly 1 pound of milk. So just, I'm going to show you some values for distillers grains in a moment here. But what he does is he uses basically a series of calculations to evaluate and identify and estimate the rate of fiber digestibility, and then ultimately estimate potentially digestible NDF. Okay, what is that? That's essentially, if you feed this feed to a cow, this is how much NDF is digested. Okay, so that essentially is giving us an understanding of just how much energy may be available to produce milk. Okay, so what I have listed here is a table on the left side with some samples that we had that were collected several years ago by my graduate student. And the total track NDF digestibility, she estimated for distillers grains, there's 2 basically locations of distillers grains tested, roughly 64, 65%. total track NDF digestibility. So is that high or is it low? What I have listed here, remember, corn silage is about 42%. So at least in compared to corn silage, it's a little higher. What about other byproducts? What I have listed here in red bars is total track NDF digestibility of other feeds, other byproduct feeds, beet pulp, brewer's grains, canola meal, and cottonseed. And you can see only second to beet pulp in this slide is distillers grains is a source of digestible fiber. And so that's really, I'm not going to talk a lot about digestible fiber in this presentation, but I wanted to identify and make sure everybody understood that distillers grains really are a source of digestible NDF, and that supplies energy to the cow. So what I'd like to do is talk a little bit about basically swapping in distillers grains from some more common protein ingredients. And so the first study I'm going to show you was a study conducted by one of my graduate students several years ago, comparing distillers grains to canola meal. I'm sure everybody is familiar with canola meal. It's a very common feed, common byproduct or co-product feed. It's about 30% NDF, which is listed here, which is a little lower than distillers grains. Distillers grains is probably in the mid 30s on average. I have 39% here. Canola meal is also a little higher in fiber, 38% crude protein compared to about 30%. Canola meal, at least by a book value, tends to be a little lower in rumen undegradable protein. Very easy to distinguish the difference between the two. Usually canola meal is much darker. If you ever see the canola seed, it's almost like a black marble, whereas distillers grains has kind of a yellow color, which is obviously indicative of corn. What about the protein and the digestibility of protein of these two ingredients? I've actually listed 3 ingredients here: soybean meal, canola meal, and distillers grains, as described by NRC 2001. I think everybody probably knows there's a National Academy of Sciences has a new publication out. These values are very similar in that new publication. But the RUP of distillers grains tends to be a little higher than either canola meal or soybean meal. The intestinal digestibility, at least based on that publication, is highest for soybean meal and lowest for canola meal. Very similar values were collected by a graduate student of mine here at the University of Nebraska, and I've got those listed here, but the two sets of values are very similar. Okay, so what I'd like to do is spend some time showing you actually 2 studies, but the first one is related to canola meal, where we've actually tracked the flow of energy. We fed 2 diets to animals, and we tracked the flow of energy when animals consumed that feed. So where does that energy go? I think anybody that has spent any time around a cow, you know that a large proportion of energy is still lost in the feces with the feces that are excreted by the animals. Generally, the animals will lose about 27% of their energy in their feces. Additionally, energy is lost in the urine, as well as gaseous losses. Those tend to be a little lower, about 5%. As listed here. Heat is also lost, or energy is also lost for heat. That can represent around 40%. And then about 20% of the total energy ends up in the melt, with about 2% in the energy. So in the study that I'm about to show you, we actually tracked fed animals a diet, and we actually tracked the energetic losses of energy in these 2 different diets. This is just a picture of our operation when we're doing this. And I will note that all of the studies that I'm showing you are with Jersey animals. But on the left-hand side is just a showing of the diets that the animals were offered in the situation that they're in. here in our situation. And then when we collect energy losses through the feces and the urine, this is a study under process or undergoing here in this picture, where feces is collected either as it's leaving the animal, or hopefully, and sometimes when it's collected on the floor, as well as catheters that are set up to do total collection of urine as well. So I mentioned some energy is lost in heat. This is how we measure heat energy losses and gaseous energy losses. It's something called the Indirect Calorimeter. Just very quickly, what we're doing is we'll place an animal in here for 23 hours. We'll run air through this system. And then over that 24 hours, what we'll do is we'll collect a subsample of that gas and we'll collect it. By knowing how much, and then what we'll do is we'll measure the total oxygen that animal consumes, the total amount of carbon dioxide that she produces, and how much methane she produces. If we know these three gases, we can use a calculation that's been around since the 60s to actually calculate heat energy production, as well as obviously gas energy losses through methane. This is just a picture showing our gas analysis system. So getting back to our study. So basically what we did is we fed two different diets, one that contained distillers grains and one that contained canola meal. There were two other treatments here, but I'm only showing these two treatments here, okay? Very simple garden variety diet that we have here in Nebraska and the Midwest. But what we did is we swapped out distillers grains for canola meal. And these numbers represent percent of the diet dry matter. It is not pounds, as many of you may be accustomed to seeing feed formulation sheets from your nutritionist, but this is percent of the diet dry matter. So about 10% of the diet was one of these two co-products. So what did we see here? What I have listed here is the digestibility of dry matter, crude protein, starch, and NDF for these two diets. And what we observed is very similar to the data that I showed you before. When we actually fed these feeds to the animals, there was a slight reduction in total track crude protein digestibility of the canola meal, as well as NDF digestibility was also lower than the canola meal. So distillers grains, in addition to be very palatable, tends to be very digestible. And in this study, data would suggest, or our results would suggest, it's a little more digestible than canola meal. What about the energy? So we went through and looked at all of those energy losses. And what we saw is, in addition to being more digestible, we actually saw, so these abbreviations are gross energy, digestible energy, metabolizable energy, and then total energy, including both tissue and milk. And I'm going to talk about this a little later, but you can see the energy for the distillers grains based on these three energetic measures are higher than the diet that contained canola meal. So what did the animals actually do in terms of performance? As I noted, they were Jersey animals. So dry matter intake on average was actually very similar, about 39 pounds per day. If we calculated energy corrected milk, that was actually also pretty similar. And then the percent fat and protein was also similar. So you may be asking yourself, okay, well, Paul, you've told me that the distillers grains, at least in this study, are a little bit more digestible, but your production didn't show it. Well, one of the things that you'll see here is an estimate of tissue energy as well. In our system, we're able to estimate tissue energy. And the animals that were consuming canola meal actually we're losing more tissue energy to support milk production, okay? And it's really important for you to understand this, because we know that you know, there is a cost to losing too much tissue energy. And so basically, in our case, the energy didn't go to milk or milk components, but we did actually have a little less loss of tissue energy. So when we look at productive energy, which includes both tissue and milk energy, we saw more productive energy when animals consumed distillers grains. So to answer that question, even though milk production didn't follow with improved digestibility, what we saw was more productive energy. Well, I know the title mentioned economics. I'm not an economist, but I was able to just run through very simple cowboy math. In fact, my graduate student, Addison Carroll, helped me with these numbers, taking the individual costs of all of these ingredients that we fed, as well as the value of the milk. And what she's done here is said, okay, well, with this 10% inclusion of these feed ingredients, what were those feed costs per day? There was some slight differences in dry matter intake, but the canola meal did result in a more expensive diet. That's no surprise. Canola meal, the price that we used was $365 a ton, which is a little more than $320 a ton for distillers grains. That these numbers may be different, and certainly I would encourage you to use the numbers that you're working with. But at least in our situation, canola meal is a little cheaper. And what does that translate to when we look at income over feed costs? As you'd expect, through these numbers and what we observed in terms of production, the income over feed costs was also a little higher when we fed distillers grains. So to this point, what do we know about distillers grains and what have we learned? Certainly it's highly palatable, and it is quite a digestible feed ingredient that supplies energy for productive purposes in the lactating cow. And it does so by being, at least in our case, and in most cases in the United States and certainly around here, it does so in a little cheaper fashion. Okay. So the next thing I'd like to do is show you a study that Addison Carroll conducted several years ago here at the University of Nebraska. Very similar to the last one in terms of how the diets were set up, but rather than comparing canola meal, she looked at non-enzymatically brown soybean meal. Again, another very common feed that's used to supply rumen undegradable protein to cows. This is a nice infographic. I'm not going to have a lot of time to show you all of the details. Very similar in design to the last one, but I'm going to show you, instead of just showing you 2 treatments, what you're going to see is 4 different rations. Okay, the first one is a control that basically had non-enzymatically brown soybean meal in it. And then what we did is we titrated in the high protein co-product and removed some of the soy pass. So this high protein co-product, which we're seeing more of this here, there's a number of plants around producing a higher protein distillers grains. And so what we've done is we've removed the soy pass and added more high protein distillers grains at 2.6% of the diet dry matter, 5.4% of the diet dry matter, and 8% of the diet dry matter. And then very similar to the other studies, we measured where energy went in the feces, in the urine, in the milk, in the tissue, as well as gaseous losses and heat losses. And these are just pictures of those indirect calorimeters that you've already been introduced to in a previous slide. So this is how the diets were set up. I guess one thing that I would note is, well, first of all, very similar, again, percent of the diet dry matter listed here. And then these are the different dietary treatments, a controlled treatment that contained 8% of non-enzymatically brown soybean meal. And then the 2.6% treatment, which a portion of this non-enzymatically brown soybean meal was removed and the high protein co-product was added. So we did this up to 8%. So 4 different diets were fed, okay? This is a listing of the chemical composition of the high protein co-product, which is listed on the right-hand side, about 52% crude protein and about 6.4% fat. So this is the chemical composition of these diets. Very similar. If you look at the crude protein content of these diets, about 16.1% of the diet dry matter was crude protein. And then if you look at NDF, very similar, but maybe slightly higher when you went up to the 8% of the high protein co-product. One of the things that I should mention here is that this product did have about 6.4% fat in it. And so if you look at the total fatty acids of these 4 diets, it did increase as you went from the control up to the 8% high protein co-product. Why is that important? We'll talk about that in a moment. But again, that's a pretty important source of energy that the cow may be able to utilize. So this is a listing of the digestibility of several nutrients, that actually more nutrients than I showed you before. So what I have listed here are the individual treatments, the control, 2.6, 5.4, and 8% of the high protein co-product, as well as these nutrients that are listed here: dry matter, organic matter, crude protein, NDF, starch, fatty acid, and energy. We can go through this pretty quickly. Actually, we did not observe any, in comparison to the canola meal, we did not observe any differences in total tract digestibility of these diets. So very similar, even though there was some slight numerical differences. Okay, well, what about energy losses, or basically where energy went? What we did see are some pretty important measures that I would ask you folks to hone in on, and these are going to make even more sense when we look at the milk production data itself. But what we did see is that the animals, as we added more of this high protein co-product, they did put more energy into the milk. The control was 23.7 mcals of energy, up to 26 mcals of energy. In addition, we actually saw some differences in tissue energy. So the control, they were in slight negative tissue energy. And then as they added the high protein co-product, that increased in these first 2 treatments and then decreased. So we saw kind of a quadratic statistical trend here. But what we saw is that total tissue energy was highest on the 5.4% of the high protein co-product. Okay, these are these measures that I showed you before: the gross energy, digestible energy, metabolizable energy, and then the net energy. So tracking with that screen that I just showed you the last time, if we looked at fractions of energy of mcals per kilogram, you'll see that the highest concentration of energy was observed on that diet that contained 5.4% of the high protein co-product, and then decreased once we got up to 8%. You may ask me why we observed this slight decrease, and I have to tell you, we're still kind of trying to think through that. I really don't have a good reason right now. But what's important to see is that the lowest concentration of energy was on that control diet that didn't contain any of it. That obviously, as it increased going from left to right, one of the contributing factors was the increased concentration of fat in these diets that was coming from that high protein co-product. Okay, the other thing that I'm just going to mention is just the conversion of energy. This was, again, a bit of a surprise to us. What we saw is animals are able to take a little more of that metabolizable energy and convert it into net energy. And we observed that again on that 5.4% diet. Okay, so this is production of these treatments. What I have listed here on the top are the treatments that you should already understand: the control treatment, as well as the 2.6, the 5.4, and then the 8% of the high protein co-product. And then listed on the left-hand side are what we'd call production variables. Obviously, the first one is feed intake or dry matter intake, then followed by milk yield, energy corrected milk, and then actually efficiency, energy corrected milk over dry matter intake, followed by protein, yield of protein, and then yield of fat. Okay, so what I will note here is what we did see is no difference in dry matter intake, roughly about 20 kilograms, regardless of what treatment those animals were consuming. If we look at milk yield, there was a slight increase as we went from the controlled, no high protein co-product up to the 2.6 and then the 5.4. So when we included 5.4% of the total diet as a high protein co-product, we observed the highest milk yield. And then we saw a slight reduction as you moved a little further. Statistically, though, I would note that this is only a trend. The p-value is 0.08, and that's actually a linear trend, okay? What about energy corrected milk? So we saw very dramatic differences. Those animals went from 34 kilograms up to 37 kilograms on these latter two treatments. So what was driving that? It was this striking response that we saw in milk fat. These animals went from the control producing milk that was about 5.05% fat up to almost 5.5. So where you saw almost a half point increase in milk fat. Why do we see that? We're not exactly sure. We're still trying to figure that out, whether that was related to the fat that the animals were consuming. The other thing that I'll mention is this high protein co-product that was being fed in this study. The manufacturers believe, and they've got some really neat data demonstrating that this feed, in addition to plant-based protein, that it also is containing some yeast cells. And so the question that we have is, are these yeast cells having some kind of effect in the rumen to improve milk fat? It's totally unexplored. It's just conjecture, but it's important to understand that not all of these nutrients are actually plant-based, but that some of them are actually coming through that the nutrients through the fermentation process. And in this case, it's the contribution of those nutrients as well as what other bioactive compounds could be there in the yeast cells, okay? So it's interesting, we don't have any rumen measures, but the question is, what could be happening in the rumen on these animals to support the milk fat? We don't have a good explanation yet. Should also mention, we saw an increase in milk protein. This is not unusual when we feed Distillers grains. As I mentioned, they are a really valuable source of energy. Protein, when cows synthesize and the mammary gland synthesizes protein, obviously it needs amino acids to do so, but the process of putting protein together and synthesizing it in the mammary gland is quite energy intensive. So anything that you do to bump up the energy supply in that cow, it's not surprising that you'll often see a blip in milk protein when you do so. The cow just has more ability to synthesize that milk protein. Okay, so what about the economics? Again, very simplistic view. Looking at the cost of these ingredients, what we did is we put a cost of the non-enzymatically brown soybean meal at $465 a ton versus the high protein co-product at about 10% less, okay? What does that translate into feed costs? So what we have listed here are feed costs for these four treatments. The control, which was observed to, because these animals ate less, was observed to have lower feed costs, $6.98. But then as you move from left to right, going to the 2.6, 5.4, and the 8%, feed costs did increase. And this was driven not only by the differential costs of these, but also some differences in dry matter intake. What about income over feed costs? If you look at the value of that milk, what we saw is that the more Distillers grains that we added into this diet we actually saw improvements in feed costs. And so, is there anything magical about distillers grains? Certainly the yeast cells that could be in this ingredient is very interesting and intriguing. But I think the value is often pretty simple. Number one, because it's a co-product, it tends to be a little cheaper than some of other co-products, as well as maybe some traditional protein feeds like maybe roasted soybean, for instance. But it tends to be a cheaper ingredient, and so is not only cheaper, but if we get some improvements in digestibility, then we can see some improvements in income over feed costs. Now, what I should mention here, a lot of people will look at this data and they'll be intrigued by it, and I think it's really valuable information that shows the value of distillers grains. But I think what I haven't done here is show you some of the variation that we see in the real world with quality of distillers grains. And it certainly does vary from plant to plant, as well as region to region. Just like anything you buy, you have to have hopefully a pretty good understanding of the source of that feed, and making sure that they're doing their due diligence in maintaining the quality of that feed. In all of these studies that I've shown you here, we fed a single source of distillers grains. We didn't get kind of an industry average of hundreds of different sources here. And so there is some variation in the real world in terms of not only chemical composition, but digestibility of distillers grains. So if you're thinking of using it and understanding it better, I'd strongly encourage you to start looking at the individual sources, try to find some chemical composition or feed testing information around that. Talk to your nutritionist about this, and get some good understanding of just the value of that, not only in terms of chemical composition, but you may use some of these methods. I mentioned the Total Track MDF digestibility method by Dave Combs. You may use some in vitro methods to estimate the digestibility of those nutrients in the feed as well. So chemical composition and in vitro digestibility may be something that will help you ensure that you see responses similar to what we're describing here. So just a summary here. Obviously, ruminants contribute to the sustainable food supply by consuming co-products, and that was that infographic that I showed you earlier. Distillers grains are a source of digestible NDF, and that is really important for supplying energy. If we look at the first study with canola meal, the digestibility of canola meal in our case was lower than the distillers grains that we tested, and this may affect the supply of energy that's that the animal actually receives, and ultimately productivity. This new high protein co-product that I've mentioned, really intriguing, shows really positive responses, certainly in milk fat, but it shows that it's a palatable ingredient that the animals consume it. We didn't observe any differences in digestibility compared to non-enzymatically browned soybean meal. And we did actually see some improvements in energy utilization, which we probably don't have all of the answers yet, but it looks like a really valuable feed in terms of supplying nutrients to lactating dairy cattle. So Fred, I think you had asked me to stay right around 40 minutes, and I think we're close to that now. Should I just turn it over to you to moderate?
Yep, you sure can. I'm going to mention if folks listening have questions, we're a fairly small group. Just unmute your mic and you can ask the question, or if you prefer, you can type it into the chat box. I want to make you aware that I've posted a survey. We hope we improve every webinar because of the information you share with us. So it's important to very short, 4 questions. The other thing I want folks to be aware of is that It is archived there at the I-29 New University website, as well as at Iowa State website. I don't see any typing going on, but I want to introduce my cohort in Minnesota, Jim Salter. Jim will be helping with the questions as well. And Jim, I know you well enough to know that you're probably going to have our first question.
Yeah, I actually have a question for you, Paul. How's life in Nebraska? Good?
Yeah, it is good. A little
Weather good?
warm here. Yeah, it's hot, but yeah, things are good.
But you know, traditionally, Distillers has kind of been blamed for low fat tests, and you know, that was initially we'll feed too much of the high fatted. So that's kind of my first question. And even typically, higher fat diets and higher fat products will hurt protein test, and you've got some pretty intriguing data that it doesn't. Do you want to explain, were we wrong before, or is there certain diet formulation that's required to make sure we don't see that decrease in fat test and also the protein piece?
Well, so distillers grains, let me say a ration formulation, a new ration, whether it's a formulation or just a new ration that you put in front of the cows that contain more distillers grains, it can cause milk fat depression. And we've done some work on that. There's been a number of people that have looked at that, tried to figure out why. We've historically seen that when I mentioned, you know, when you're thinking about using this ingredient, to have a really good understanding of the chemical composition of the distillers grains that you're feeding. And I know, you know, 15 years ago, when we fed a lot of this high fat distillers grains with about 12% fat, we were seeing in the field a lot of milk fat depression, and that simply was because of all of the unsaturated fatty acids that were coming from the corn oil in distillers grains, and it was just thrown in. It looked like it was supplying a lot of energy, but it had some negative effects on rumen fermentation and the bioactives that were produced through that to really reduce milk fat synthesis. So it can do it. And certainly there's some diets that are more inclined to even having more of a problem if you've had a really high starch diet. So if you had a lot of corn oil and a lot of starch, that really seemed to set us up for milk fat depression. So first of all, that is real, but making sure you understand what you're working with, and working with the nutritionists that understand the different levers to pull when you're actually putting that ingredient in. Now, the first thing that I'll mention is the industry has found other homes for a lot of that corn oil. And so we're seeing distillers grains much lower in fat. So that's the first thing. We're seeing less of the corn oil in distillers grains. So right away, that's kind of added a level of safety when we're feeding distillers grains. There's just less corn oil. But just making sure that you work with the nutritionist who's able to track these fatty acids, I think is also quite useful and important. So it can do it, but I also think there's been a number of studies. You see the studies that I've shown you here. Certainly you can incorporate it and actually avoid milk fat depression, but you certainly need to know what you're doing and understand what you're feeding. So that was the first question. You had another one, Jim. I can't remember what
about
that was.
Protein. Typically, when you feed high, is that just balancing for amino acids? Is that what's the key to making good protein?
Right. So that's a good question related to the protein. So we're still trying to understand amino acid requirements for cows. The new NASEM model, I think, is really helping us, as well as some of these other models. But yeah, we have seen when you added distillers grains, you'd see a drop in milk protein, and when that happens, it's been speculated that we know corn is low in the amino acid lysine, and so it's been speculated that the animals then, as you add distillers grains, become short in lysine. But I think it's important to understand that's not the case for all diets that contain distillers grains. There's other ingredients in the diet that contain lysine. And so those animals may, there's many cases that all of the cases that I've shown you here today, we didn't see drops in milk protein. And so our diets, right from the get-go on the control, we evaluated them for amino acids. And so none of them were short with the with lysine. And so I think that's the other thing that nutrition, when you're thinking about using this ingredient is have your nutritionist look at the lysine and say, okay, if I'm adding the distillers grains, yeah, maybe my lysine content is going to go down, but is it going to be deficient? And I've shown you some examples where, yeah, lysine concentration maybe went down, but we didn't see any negative effects on milk protein. But if you just throw it in haphazardly, you can get some of these threats of milk fat depression and reduction in milk protein.
Paul, if I can jump in here for a second, can you give me control back to?
Yeah, I thought I did. How do I do that? How about if I just stop sharing?
There you go.
Yeah.
And then let me know if my screen.
And let's see.
Is that in the bottom of your screen, Paul? Or,
yeah. Okay, yeah. Okay, I think I've stopped sharing. Do you have it now, Fred?
Jim, can you see?
Yeah, I see the,
okay.
Yep, there we go. Slideshow.
Thank you.
If nobody else has a question, I have one more. And you mentioned these, Paul. What about these new products? I see one, Capolet's got one, you've got Nova Meal that are out there. They're kind of deep fatted distillers grains. Do you have any comments on if there's farmers listening or nutritionists, do you have a preference? How might they be used differently?
Yeah. Well, I think, an advantage of some of these branded products is that you've got a company to talk to about, the specifications of that ingredient. So there's many different out there. We obviously don't have time to talk about all of the ones that may be available, but when these branded products arrive, on the farm, usually there's a company that obviously has got them to the farm and has been tracking quality control of them. And they should be able to give you a reasonable understanding of the chemical composition and the digestibility. I think that's an improvement from the Wild West when, these products were just arriving from who knows where. And so having these companies that are, really understanding the process where these were produced and then ultimately delivered on the farm, I think that brings tremendous value in understanding these feed ingredients.
Are most of them the deep-fat soy products, Paul, or are there other ones out there? Or
Yeah.
other kinds of corn byproducts? You could even comment on like corn gluten feed. I don't know if you've done a lot of research on that, but where do these, because there's a lot of corn byproducts that are out there.
Yeah, certainly. So it's hard for me just in a quick soundbite to talk about all of them and give a good understanding of all of the feeds that are out there. But certainly if you look at one of probably the most common branded ingredient is one that is lower in fat. And so that's certainly what they've done is they found a different home for the fat and they may be even removing the fat further and then making that feed available on the farm. So that's a very common one. The other one that I mentioned is high protein. Without going into the engineering, that tends to be a little more concentrated in protein, not only, as I mentioned, the plant-based protein, but some of the yeast that is actually added back from the fermentation process. And so that's a fairly unique one. And then you have corn gluten feed. We were doing these palatability studies. What we observed is corn gluten feed is also an extremely palatable ingredient as a feed itself that tends to also supply a lot of energy. It tends to supply less bypass protein than traditional distillers grains. So you may be, looking at, replacing maybe some forage, maybe a bit of corn, and maybe less protein ingredients with corn, like bypass protein sources with corn gluten feed. So I think that's the big thing to recognize, is that corn gluten feed tends to be a little lower in bypass protein than distillers grains.
Okay, I'm not seeing any more questions coming in. I don't see anybody on mic or muting their mic. At this point, any closing thoughts, Paul? Just something you want to
No,
send
I
them
just,
away with?
well, Fred and Jim, I guess I just really want to thank you for this opportunity. I mean, this is not old school extension, right? We're reaching across state lines electronically. We didn't do this when I started, and I think the same can be said for your career. So I really appreciate this opportunity, and then making this available. I'm just not at a state office somewhere in Nebraska, but hopefully we can share this with other people. So I just want to thank you for this brave new world of extension that you folks have set up and are running here. So thanks for the opportunity.
Well, thank you, Paul. Nice job.
Yeah.
We appreciate bringing this information to us. Just one comment on the idea that we are now worldwide. You know, of the folks who registered, we had 3 foreign countries represented and a multitude of states. So we are always excited when we can take great information and distribute it across the globe. Thank you again for the time, and thank you to the folks who will be or who enjoyed the program today. I might mention that we are taking a month off in August. State fairs seem to take a priority for a bunch of us, so we will see you again in September. Thank you, and
Great.
we'll be
Thank you.
in the program.